Hey everyone, welcome back to the lab. On behalf of Forge College, I'm super excited to guide you through today's explainer. Look, we're diving into what I like to call the ultimate safety protocol for comparing blockchain account models. Because, let's be real, if you just try to compare Ethereum's stateful accounts directly with Bitcoin's UTXO model without a rock-solid methodology, yeah, you're not exactly doing science. You're basically just causing a statistical chemical explosion. So let's throw on our safety goggles and figure out how to frame a comparative analysis without, blowing up all our data. So right off the bat, how do we actually pull this off? How do we compare outcomes across entirely different account models? As we just said, mixing Ethereum and UTXO blindly is a one-way ticket to meaningless results. But hey, we aren't walking in unarmed here. Think back to our previous lesson on sequencing, nonces, and preparing for the comparative capstone. That gave us our very first safety tool, right? Understanding how nonce-driven transaction ordering actually dictates the sequence of state transitions. Now we're going to take that tool and use it to build our entire framework. All right, here's a quick look at the lab manual for today. We'll kick things off with the controlled experiment, move into the four-phase workflow, cover sourcing your data, hit the rules of normalization, and finally, wrap it up with your capstone plan. Let's jump right into section 1, the controlled experiment. Now, this isn't just a catchy title, it's literally our core mental model for this capstone. You really have to think of a comparative analysis as a series of strictly controlled experiments. Every single observation you make, it has to point back to a plausible, logical, causal chain. We can't just stare at a failed transaction and play guessing games about what happened. We need to know for a fact that the failure was caused by our specific test conditions, not just some chaotic random confounder lurking in the dark corners of the mempool. Here's how we break down the scientific methods specifically for Web3. It's all about isolating those variables. On one hand, we have our independent variables. These are the things we actively manipulate, like the account models themselves or non-sequencing. And on the flip side, we've got our dependent variables, the things we're actually measuring, like operational outcomes and concurrency behavior. By isolating something like, say, a single account sequential submission versus a concurrent nonce race, we can measure the exact operational behaviors that pop out. No guesswork required. All right, moving on to section 2, the four-phase workflow. This is our standard operating procedure, the exact steps to transform those high-level curiosities into rock-solid, measurable tests. We've got phase 1, nailing down your question. Phase 2, defining the metric. Phase 3, sourcing that data. And phase 4, the actual execution. By following these chronologically, you'll produce the tangible artifacts you need to carry forward into your final report. Let's break these down. In phase 1, our research questions need to be incredibly specific, like laser-focused. We have to name the models being compared, pinpoint the observable behavior, state the expected difference, and define the real-world practical impact. A quick warning, though, keep these questions super narrow. Try to avoid those sweeping philosophical statements like, which model is better? I mean, it's a great question for a late-night debate, but it will absolutely ruin a data-driven experiment before you even get started. Okay, moving into phase 2. Remember, a question without a measurement is basically just an opinion. We have to map each of those research questions to a concrete, time-bound metric, making sure to capture both raw measurements and derived statistics. A great example of this. Think about measuring the percentage of transactions failing due to nonce mismatches, specifically within a strict 60-second submission window. Now that is a metric we can actually test, track, and graph. That brings us to section 3, sourcing your data. So now that we have these tightly scoped questions, where do we actually go to dig up the data? Well, different metrics require vastly different data fields, which means completely different sources. Look at this table for a sec. If you're hunting for a nonce mismatch failure rate, you're going to need the transaction hash, the sender, nonce, status, and the block. That stuff is pretty easily grabbed from an archival RPC, so we call that a medium retrieval complexity. But if you want something like the median confirmation time, oh boy, you'll need local submission logs mixed with RPC data, which immediately spikes your retrieval complexity to high. The big takeaway here? Always map this out before you write a single line of code. Finally, we hit phase 4, which is all about execution. You're basically writing a reproducible checklist script here. Set up the snapshot, inject your concurrent transactions, wait for block M, capture the post snapshot, and run your assertions. And the key word there is reproducible. Any other analyst should be able to look at your script, recreate your exact conditions, and verify your checks independently. Let's be real. If it's not reproducible, it's not science.
All right, on to section 4, rules of normalization.
This is where we tackle what I think is the hardest magic trick of the entire lab. Comparing Ethereum's stateful accounts to Bitcoin's stateless UTXOs without accidentally comparing apples to oranges. To pull this off gracefully, we use 3 distinct classes of comparison criteria: semantic parity, operational behavior, and forensic traceability. And here's the kicker: a truly defensible analysis has to pick criteria from all 3. If you ignore even one of these, your comparison is structurally incomplete right out of the gate. To actually achieve that balance, we rely on a normalization rule. Basically, this is an explicit translation method used to map a concept from one account model over to a comparable construct in another. Think of it kind of like a currency exchange rate, but for blockchain data. For instance, you might sum up all the UTXO outputs controlled by a specific locking script at block N just to create an effective account balance. By building this artificial construct, it perfectly mimics an Ethereum account balance, which lets us actually run the math side by side. Let's take a closer look at forensic traceability for a second. When a failure happens, your post-failure artifacts are going to look completely different depending on the chain. On Ethereum, you get storage proofs, logs, and transaction receipts at block N. But with UTXO, you're looking at Merkle branch evidence. So, to fairly compare them, you need to synthesize a normalized operation trace object. This object holds timestamps, involved keys, pre-state, and post-state data, basically giving you a standardized way to evaluate the recoverability of both models fairly. But here is the most absolutely crucial point: honesty. Sometimes a metric just cannot be fairly normalized, and that's okay. When that happens, you need to practice honest normalization. Seriously, do not force misleading numbers just because you want a pretty chart for your report. If it doesn't fit, simply record it as a model-specific behavior and analyze it qualitatively. Capturing these qualitative differences, it actually shows a much deeper, more nuanced understanding of the underlying architecture. Okay, we've made it to our final section. Section 5, preparing your capstone plan. All right, it is time to suit up and actually put this methodology into practice. Here is your action plan. First, convert all your artifacts from this lesson into inputs for the next stage. Second, take your prioritized questions and map them to 1 to 3 measurable metrics. Third, attach your data sources using that sourcing table we looked at. And finally, get to drafting your stub query patterns. Make sure you bring these mapped metrics and query stubs to the next stage of the course. That way, you'll have a rock-solid foundation ready to build on. As you head into your capstone work, I want to leave you with this one final critical challenge. Are your independent variables strictly controlled? And are your normalization rules completely honest? I want you to ask yourself that question every single time you look at your data. Seriously, make it your mantra. Now, if you want to dive deeper into this and check out other fascinating Web3 topics, be sure to visit forge.college. On behalf of Forge College, thank you so much for watching this explainer. Keep experimenting, stay curious, and we'll see you in the next one.